Okay, good afternoon. Today we're going to delve into the quantitative, more of a quantitative treatment. Basically some good fun algebra that everyone should be able to do no problem. We'll look at structure and how surface area is important in nanomaterials. One thing to remember is earlier we claimed that nanomaterials have different properties than bulk materials. So we have to wonder why they have different properties. For example, when particles get smaller, what do they do that causes different properties? Well, definitely electronic structures can be altered, but more importantly, the surface has to be mitigated. There is a phenomenon called excess surface energy, and this excess surface energy causes nanoparticles to be unstable. So nanoparticles are, we can call them metastable. They're searching constantly for stability. How do they find stability? But before we're going to go into energy mitigation in a little bit. But first, let's study the structure. We'll study the surface first, and then we'll look at clusters later and delve into what are called magic number clusters. And then at the end, time permitting, we'll look at the carbon nanotube and these other kinds of interesting materials. There's some brilliant mathematics that they've done in vectors and other kinds of topology, things like that. Okay, so let's just get started with that. And if we have time at the end of it, we'll go back to yesterday's slide and finish that business section, which is, I think, very important to many people. Okay, we look at our agenda. We'll look at collective surface area. And basically, I think we're going to just do the first 5. The other things we'll leave for another time. I don't think we'll have time for all of it. So we're looking at what is called collective surface area, and we mentioned briefly yesterday how that can be quite enormous for nanomaterials. So we'll just reinforce that concept a little bit today. Then, very importantly, we'll look at particle shape and the relationship between surface and volume. It's meters squared divided by meters cubed, so it's reciprocal meter relationship. But that is very important in terms of understanding how this kind of surface to volume ratio translates into energy stability. So something with extremely high surface to volume ratio might be more energetically unstable than something with a very low surface to volume ratio. These things we're going to get into too. Crystallography, which is the most brief introduction to crystallography. Have you had any crystallography at all? What that is basically the structure of the crystal. We can look at it here. It's the way this is put together. I can put atoms on top of each other. That's a different structure. I can put different phase shift. That's a different structure. So there's many different structures that atoms and molecules can take. In your case, polymers can also be somewhat crystallized. Liquid crystals, for example, things like that. So you'll have a brief enough introduction so you'll be able to understand that. Then lastly, the carbon nanotube. It has a honeycomb structure. We already saw that, and we understand that carbon nanotubes are some of the strongest materials. Tensile strength that's very phenomenal, but its vector relationship and how you can calculate all the properties of carbon nanotubes. We'll try to get into that too. Okay, collective surface area again, just so you can get a flavor of what can happen if I take a solid sphere. I break it up into smaller spheres. If I add up the surface area, there it's going to be much larger than here. And as you can see, as you go smaller and smaller and smaller levels, the surface area increases Actually, they're just goes like this. So definitely once you get past 10 nanometers, it goes. Remember, I said that nanomaterials are living on the curve, right? Everything, every property you can imagine is just. Bulk materials are very, very boring. Well, bulk materials are what makes us build automobiles, right? Because if the melting point in bulk materials went like this, we would have cars melting on the road and things like that. So bulk materials have to be very stable, but nanomaterials don't. You say, okay, well, what we can't use them then? Well, we can stabilize them. We'll put them in a polymer matrix. We'll make that polymer better. There's a lot of coatings on automobiles nowadays that have silicon nanoparticles embedded in the polymer. It's basically, you can't scratch it or anything. Others have zinc oxide that absorb the ultraviolet light, and it keeps the polymer much safer and stronger in the long term. So collective surface area is just simply add up all the surface areas of the broken up pieces. And by the way, okay, going from here to here, does it take energy to do this, to go from here to there? Does it take energy? Yes. If I want to break up this table, I have to use energy. Going the other way, you technically would give off energy. So this way, you break up energy. The other way, you give off energy. Examples.
Is that almost a universal principle that to create more, I guess, surface area to total volume, you need energy, right?
Absolutely, because basically you're breaking bonds.
You're breaking bonds.
If you're breaking bonds, you have a solid. I'll have an example with water. I have a drop of water and I want to aspirate. That requires energy.
But on the macro scale, you have 2 drops of water. It's easier for them to get together into bigger ones.
And what happens? Does it give off energy or does it cool?
Okay. So
see which way does it go? Huh?
Right. Gotcha. So if you go the other way,
when you're putting it together, actually it gives off heat.
So the intuition makes sense. But it's easier to get together.
To break it up, you have to input energy. And that's actually cooling, because heat is absorbed from the environment. That's correct. Okay. When drops are coming together, you are making bonds and you're giving off energy. When you are breaking up the water droplet, you're sucking energy from the environment, and that's
cool for us. Yeah.
It's always been. You have to figure out how does this work. Okay, here's a graph. We're just dividing things. These are great things to program. And I did it by hand. And I have my little kaleidograph. It's one of these graphing programs. And it has a little formula entry, and I can do the formula. But it would be nice to have more of a universal. We talk about this kind of stuff soon. Anyway, look at here's a sphere. And these are equivalent volume. So all of these three geometric figures have equivalent volume. Okay. However, we can see that we have the same number of divisions into equal divisions, or whether they're tetrahedrons, cubes, or spheres, that the tetrahedron has the highest collective surface area. All right, even though it has the same number of particles. Okay. The next one is the cube. The third one is the sphere. So the lowest surface volume or collective surface area is given by the sphere. Why is that? What trend do you see here? What do you see? What kind of trend do you see from a sphere to a cube to a tetrahedron?
It probably has to do with packing problem.
Well, actually, it's more simple than that. Here, it's obvious just by the names. Tetrahedron is what? 4 sides. Cube, 6 sides. Sphere, infinite number of sides. Yeah. It's basically infinite number of sides. So it seems like the more sides we have, the better our surface area is, or actually turns out to be surface to volume ratios. So this trend is just an indication of what's to come. You want to understand? Okay, you can see. And you just imagine a tetrahedron, 4 sides, 6 sides, an infinite number of sides. A cube octahedron would be where in this graph? A cube octahedron has how many sides? You start with a square. A square has 6 sides. Okay, cut off all the corners. That's 8 sides. Total 14 sides. Where would it be on this graph? It would be right between the red line and the sphere. I predict that, and we can, with Dr. Hornyak, we can prove it very soon. These kind of things are really good pedagogy. Okay, so this is just a preview. We'll definitely have more of that later. We talked about porous aluminum oxides from anodizing aluminum. And we have a lot of holes. And you can see that there's some pore channels. So this kind of material has what we'll call interior collective surface area. The other ones were exterior. We looked at the exterior of the polygons, right? But these membranous materials that are porous, their surface area is inside the membrane. Okay. So the surface area is between the columns there, right? That can, if the diameter of the pore channel is say 20 nanometers, and the membrane is 10 microns thick, which can happen, that's an incredibly high aspect ratio column, right? And then you have a square centimeter and the porosity is about 50%. You can calculate the internal surface area. It's a lot of algebra, but you can a lot of bookkeeping really more than anything, but you can calculate the internal surface area of that. And we worked, like I said, I did my dissertation with this material, and we made many different, all the way from a few nanometer pore diameter to 200 nanometer pore diameter. And so which one would have a greater surface area? Let's say the porosity is the same. Let's say it's 50% for all of it, which means 50% of the membrane is porous. So it doesn't matter about your pore size, 50% porous. Which one has a higher collective surface area, the 200 nanometer diameter pore or the 2 nanometer diameter pore? Which one? Outside right? The smaller one always has a higher, because there'll be a lot more of them, even though it'll add up to 50% porosity. The smaller one will have a surface, internal surface area. Now these guys here, these pore channels are on the atomic level, basically, way less than a nanometer. And these are called, again, we look at the metal organic frameworks. There's a lot of polymer business involved with metal organic frameworks, because you use organic chemicals with different metals to anchor the corners and things like that. And it's a very, very, very hot technology now. And they're using it for many, many different applications. Okay, so this is what we'll work on, the internal process. So specific surface area, I'll just introduce this right now. It's very important in the catalyst industry. It's because you have a gram of material and you want to know what its surface area is, internal or external or both. So we have what's called the specific surface area, which is simply the meters squared per gram of material. So the word specific means that it's specific for a material. So I can have a catalyst made of, by the way, gold is inert, right? Basically, it does not react. However, as a catalyst, it can react. When it's 5 nanometers, it's a catalyst. Okay, gold is all of a sudden a catalyst. It reacts like crazy. Why? Why? Well, its structures, electronic structure is now different. Plus, it's starving for bonds. It's unsaturated on the surface. So nanomaterials are always looking for bonds. Any surface is. The surface is looking for bonds. That's why you have oxidation. Here, this is painted, I think, so it's stabilized. Polymers are saturated. So they're not looking for more bonds. That's why paints work. All right, so here we have the bond length from here to here is 0.143 nanometers. 142, I guess. Take your pick, doesn't matter. And we're saying that there's a third. There's 2 atoms per hexagon. It's not the unit cell for this kind of structure, but we're going to use it today as a unit cell. A unit cell is simply like a brick. So you can build a material from a unit cell. All will be identical. Nothing, everyone understand that. Yeah, it's just a basic unit cell from which we can build a whole material. So each hexagon contains 2 atoms, the rest is just algebra and geometry. Very simple. Okay, we just area of the hexagon, right? You can derive that, or you can actually just take it out of a book and we figure out that number. My math is hopefully correct, but you can always check. So this is how big the area of the little hexagon is of graphene. By the way, this is called graphene. Graphene. Okay, it's 1 layer of graphite. So I take graphite and I can put tape on the graphite and pull off 1 layer of graphene. That's how they do it. It's the most primitive way, but it works, right? So this is called graphene.
Is there a regularity between layers, or
It's again another, it's AB structure. This is an ABC structure. We will build that from 1 atom and you can understand it perfectly in a few slides. But graphite is simply alternating layers of graphene. The bonds between the layers are not very strong. The bonds this way are very strong, but you can tear off a layer no problem. Okay, so we have this equation, we calculate the area, and then next we figure out how many grams 2 atoms weighs. We know it's 12 grams per mole. Everyone know what a mole is? You had chemistry, okay, good. Well, of course. Dr. Punjab, you understand the mole. You had chemistry too.
I think
Everybody, okay, good. 6.022 times 10 to the 27. Giant number. Okay, so we have the grams, we have the meters squared. Let's see how much it is. Okay, now we have 2 sides. So if we have the area on one side, we have the area on the bottom. So we have no volume to speak of. Basically, atomic layer thick. Our surface area is 2,627 meters squared per gram. That's gigantic. 2,000 meters squared is bigger than 3 houses. That's a lot or more, I think. Well, 14 tennis courts. Here we use the tennis court again. Okay. So 14 tennis courts, just 1 gram. You know how small a gram is? It's nothing. It's just a little pinch. So we have this much surface area. This is very important when you evaluate catalysts. Catalysts must have a high collective surface area, stochastically, statistically speaking, right? If I want to change react with a gas in a catalytic converter, I need to have a lot of catalysts. If I have 1 big catalyst, which won't be a catalyst because it's too big, catalysts are small. They're small for a reason, and we're going to get into that. But if I have 1 big catalyst, the chances of how many gas atoms I'm going to react with, not very many. But if I have a lot of gases, fill this room with, I'll react with all the gas. So very important, especially in the catalytic converter of your automobile. Okay, I think collective surface area is straightforward. We don't have to go on that anymore. Good question, yes.
Is carbon nanotube catalyst?
You know what, that's a perfect question. It has electronic capability. I'm trying to think if I've ever seen a paper where it's a catalyst. Oh, you got me. I have to look that up. It's small enough, but it's saturated. Its problem is not looking for bonds. Its problem is bond strain. So graphite is the most stable form of carbon, okay? If I start bending it, it's all saturated. In other words, every bond is fulfilled. This guy, breaking anything here. Which atom here, this is gold, let's say, which atom, there's many kinds of 5 kinds of atoms here. Which kind of atom has the highest number of broken bonds?
Right.
Vertex, right? Vertex. The next highest, the edge atom, right? Next highest, face atom. So carbon nanotubes don't have that problem. Their problem is they're unstable because bond strain. When you take something flat and make a circle out of it, you're adding a lot of strain. So is it a catalyst? I don't recall reading papers, but can you look at that? Say carbon nanotube and then catalyst. It may catalyze something. It does have electronic structure. That's something that it does have because it has the double bonds on the surface. So there's a lot of what are called pi electrons floating around on the surface of the carbon nanotube. So it's where's the peak? All right. Really good question. Now we're getting to what's called surface to volume ratio. We are hinting at it for a while now, so let's get into it. We are interested in how surface to volume ratio changes as a function of particle shape and size. Very simple thing. We're now getting into geometry. Okay, we did some algebra, we're going to do more algebra and now some geometry. As a particle gets larger, the surface to volume ratio decreases. This is why bulk materials are basically stable, because their surface is very small compared to their bulk. The only thing, even gold, however, has a very thin oxide layer on its surface. So gold is still, even though there's a little bit of less surface, the gold is still looking for something to react with, and oxygen is always there. So you form a little oxide. Copper, very strong oxide, right? Things like that. Once the oxide is formed, it's stable. Shape. Particles with higher symmetry have lower surface to volume ratios. So the sphere has the lowest surface to volume. It can't do better than that. Okay. Then other counterparts with this of the same mass. We're always comparing the same volumes, same mass. Why is this important? If flat thin film will have different mechanical, thermal, optical, and electronic properties than a large sphere of the same material. So we're going to look at, for example, a sphere and then making it into a pancake, making it into a ellipsoid. All of these things have different properties because of their shape and size. I mentioned briefly yesterday that we looked at the optical properties of gold that we fabricated inside these pore channels. Some of them were very long cylinders, some were spherical particles, others were flat pancakes. And I said all of them were different colors. Remember that? That's an absolute proof that size and shape matter. Okay. And it does matter in nanomaterials. That's what makes nanomaterials so good. Okay, so SV ratio, very simple, straightforward. Meter squared over meters cubed. So our unit always will be 1 over meters. And we look at, this is particle diameter, and we look at it this way. Actually, it's smaller and smaller till we don't surpass usually 1. So if you have one, you're basically volume on the surface of the same thing. So that's, again, living on the curve. This is what we're calling living on the curve. Now, this is very true of a lot of different kinds of nanomaterial behavior. So particle surface, right now we're just doing pure geometry, pure math, but always remember that particle surface relates directly to particle energy. Okay, so look at this. Now, surface to volume ratio on the shape of a particle. Here we normalize the surface to volume ratio of a cube to that of a sphere by setting the volumes equal and then putting everything in terms of either A or R. R is the radius of the sphere, A is the side of the cube. This is again, these kind of things are going to be so good for us. Okay, so you go to read volume of the cube, right? No big deal. The surface area of a cube is just 6 times A squared. Cube has 6 sides, each one is A squared. Volume of a sphere, 4/3 pi r cubed. Surface of the sphere power. Sorry, but very, very long ago you took algebra, right? So the volume of the sphere, volume equals the volume of the cube. So you set them equal, and you get radius equals 0.62 A, right? Simple. And now the surface of the sphere, you want that in terms of A. So it's 4 pi 0.62 A squared. Gives you 4.83 A squared. Again, just working through that. And we set those two equal. There's a few different ways to approach this, but this is one way. And we find out the answer is 1.24. What does that mean? That means the cube of the same volume as a sphere has 1.24 times more surface than a sphere. Simple little geometry, but it's actually very profound when we look at energy and other properties of nanomaterials. And think about this. What atoms on a cube are the most unstable? Which atoms of the cube are the most unstable? Take the obvious truths. The corners. When you have an ice cube, right? You guys even know what an ice cube is. Everything is crushed ice now, but ice cube, you have it in a freezer, and you take it out. When it starts melting, what does it start looking like? It gets rounded, it starts looking like a sphere. So an ice cube melting, it's not going to melt as a perfect cube. It becomes a sphere. That's kind of interesting. There's energy in action right there. Water likes to be a sphere. Doesn't want to be a cube. Have you ever seen a cubic raindrop? It's all spherical. Spherical. It's the most energetically stable form of. So anyway, here, a cube of equivalent volume, 1 time more surface area than that of a sphere. Symmetry offers more degenerate states. The energy is distributed more evenly. There's no discrimination which one is better or not. It's lower. Overall lowers energy. And again, let's just reinforce minimal surface area leads to minimal surface energy. And extensive thermodynamics, extensive property in thermodynamics simply means you can add them up. Like the number of trees in a forest is an extensive property. I have 10 trees, I have 10 more, now I have 20 trees. Intensive property is always something per something. Like density is an intensive property, grams per cubic centimeter. So there are two things in thermodynamics. And by the way, nanomaterials will violate both of them. Why do intensive properties change in nanomaterials? Well, because the whole structure changes. They're trying to compensate for their surface lack. They're looking for excess surface energy means I want to make more bonds to be happy. Okay? So these kinds of things, intensive properties are definitely changing. The density of a nanomaterial is maybe not the same, like density of nanogold may not be the same as gold. Extensive properties it violates that too, but that's a lot harder to explain. So, okay, so extensive thermal variable is dependent on how much material there is. Okay, so that's the sphere, remember that, okay?
It's a good question.
Yeah.
But the thing is with cube, you have more area, right?
Yeah.
Sorry, more area per volume. And you also have more packing tightness, right? There's no waste space. There's
You
no-
know, so
you know,
right now, we're gonna get to packing soon. Right now, don't worry about packing. This, obviously, this is not 100% packed. This kind of structure has 74% packing. In other words, there's 26% of space inside the structure. That's but we can say if we make it both out of FCC structure, we'll get into crystallography in a minute. That's another variation to this whole thing. There are approximations that can calculate the number of atoms that include packing fraction. And from there you can calculate surface to volume ratio. We can actually calculate absolute surface to volume ratio here, because we know exactly how many atoms we have on the surface and the volume, which is all of it. So these things, I mean, the question is good, because there may be different, you know, if it's, we're going to say they're the same material. We can say they're both gold, and they're both packed the same, and we can calculate. Again, we can do that on Wolfram. But that's true, that's a factor. Very important, actually, because it means that material, some materials are packed only 0.6%. I mean, pardon me, 60%. For example, if I were to take these ping pong balls and just stack them on top of each other directly, A, that's a different kind of packing.
you can lose it.
There's 40% of space in those, and it's less stable. These are close packed, so they're packed as tight as they can be. Okay. All right, now here comes our problem. Now there's going to be an assignment, and you can use your computers and everything. So pay attention how this is done, because you're going to have to do a couple of others yourselves. All right, so we want to do the surface volume ratio of a right rectangular solid. Now, I thought this was a nanotechnology class, right? Simply going to do some algebra, okay? But these, I'll tell you what, why these things are important is because physicists and chemists have to use these numbers when they model materials. So they have to know how many atoms are in here, what surface shape is it, what the ratios are, things like that. So even though it's, like I said, nanotechnologists, you have to be a mathematician too. So we decided to do that today. So I can be, now we're going to assume these are all the same volume. Okay, so the mass is the same for all three of these shapes. Here you have a plate, here you have a cube, and here you have more of a skyscraper, yeah? So all of these three things, do they have the same surface to volume ratio? No. Which one has the highest surface to volume ratio? Actually, you will not be able to tell. Okay, let's show you why. Okay, now this is more complicated than the sphere, but we'll step on through it, and this is where you can plug this into your. In fact, I want to see it, and I worked this out by hand. But if you guys have a computer that you can do any math with, I'm sure that will work. So volume of a rectangle is a squared h, right? Simply the height. We're going to say h is height, a is, and by the way, we're doing a right rectangular solid, which means the base is always going to be square. If you want to do the rectangular base and a rectangular top, please go for it. I think maybe Wolfram can do it. That would be no one's done it. Okay, this is kind of stuff we can do. But we're going to just leave it at a square base and a rectangular solid, just going straight up like a skyscraper. Okay, so we know the volume of the rectangle a squared h, and the surface you have 1, 2, 3, 4, 5, 6 surfaces. 4 times AH, that goes around, and then 2A squared. You know, A squared on the bottom, A squared on the top, right? So the surface to volume ratio of a surface of a rectangle, but it's simply these two together. You do your algebra, 4/8 plus 2/h. Ultimately, you want the x-axis to be aspect ratio, which is h/a. All right. And you want the y-axis, we're going to have to graph this too. And your y-axis is going to be the normalized surface to volume ratio of the solid rectangle to the sphere. And that's going to be the y-axis, the x-axis will be your aspect ratio. All right. So there's our expression for rectangle, and then we do the same thing for the sphere. We find out that surface to volume of the sphere is 3/r. Okay, so far. Now, next we convert radius into right rectangular and solid terms. So again, the volume of the sphere is the same as the volume of the rectangle. Now there may be an easier way to do this, so if anyone finds an easier way, by all means. So that, and if any mistakes you see, please feel free to mention. So we convert, we say that the volume here is equal to the volume there. R equals 0.628 to the 2/3 times h to the cube root of h. And then now we substitute this in here, we get an expression for r. Our goal is to eliminate r from the equation. That's going to be the normalizing factor, but we want it out of the equation. So we divide this by that value, and we get r equals 0.628 2/3. I don't know if I did that right. Okay, you'll have to go through that. Looks like I got the same answer. Okay, let's just, I'll get the final answer correct. Anyway, check all of this, please. So, the surface to volume of the rectangle divided by the surface to volume of the sphere is this. And then we get that expression. So 4h plus 2a times 0.62 2/3 h 1/3 divided by 3ah. And we have to keep on expanding. I don't want to say all these things, but you can see how we're just now expanding everything and trying to gather like terms, typical algebra stuff. And we put all the, here's this number 1.24. Where have you seen that before? Where have you seen the number 1.24 before? The square, right? The ratio of the square to a circle, a sphere. So it's kind of popped up. It's kind of interesting. Okay, so we keep on going. And, oh, look at there's a number. And we get an equation. Okay, all constants are grouped, and we have that equation. But we want to reduce the equation to one variable, so we want it done h/a. So we say the answer is, look, our equation for the normalized surface to volume ratio is 0.413 times 2 h/a cube root of h/a h/a or minus 2/3. All right, great. We've achieved this. Now we want to graph it. What is this going to look like? Okay. Now, who would have ever thought that this is the aspect ratio, and once it gets really low, the plate goes crazy. Look. So let's just take the log of it. Log is a nice way to always make plots look simpler, right? And we see that the aspect ratio goes crazy on this side and much slower. You know, I'll tell you what, I cannot explain that. I don't know, I know it's part of the mathematics, but physically, I can't say why one would be so different. I mean, I would expect it to be more equal, right? But it's not. So anyway, you look at this, here's the aspect ratio, obviously the log, if it's less than 1, it goes to negative, right? So here we go, we look at that, and then we say, okay, now we're interested in this value. How do we get that? Well, you've had calculus, right? Everyone here had calculus? Okay, you take the derivative. Okay, we'll take the, what do you think that will be? What will this aspect ratio be? Looks like it's between 1.5 and 1. What do you think that will be? 1.24. So it's a roundabout way to show that the square is the most stable rectangular solid, the cube, I'm sorry. So we take the derivative, normalize of the normalized, etc., dx by dx, and we found that x equals 1 and h must equal a. And we put it into our equation, and we get 1.24. So that's kind of cool. I think, we kind of expected that, but it's still good to see the relationship all worked out.
I haven't done the graphics, but very sure that if you move as you move the height, controlling for volume, the surface goes up.
Wow, yeah.
Based on similar kind
Oh,
of thing.
Oh, I can't wait. That's going to be
I
wonderful.
have to do the graphic for you.
So 1.24, it kind of showed, already proves that the cube is the most stable rectangular solid, it is the minimum between, that's what we kind of expected. All right, you guys, assignment. And you can do this, you can turn it in any time, and you can send to me, or you can prove it yourself. It's a good thing. Now we have 2 things. Do the calculation for a right cylindrical solid and a cone. I'm not telling you, the cylindrical solid is very doable, but the cone is a bear. Okay, it's murder. But if you can get a computer program to do this. So here again, when we have a cone, how is it different from a rectangular solid, just in terms of symmetries?
It's got more symmetry.
It has more symmetry. We're actually losing 4 sides. We still have a flat surface on top and a flat surface on the bottom, but we're losing 4 sides. We just now a circle.
So it'd be less efficient,
So it's going to be better, I mean lower.
lower.
You would imagine it's lower than a rectangular solid, right? Remember, sphere is the lowest, right? So it's going to should be lower than a rectangular solid, right? Because it has more symmetry to it. So, but do the calculation, it's very similar to a rectangle, okay? Except you have to do the circle now. But let's do the same thing for a cone. You can do it too if you want. The cone has one more variable, right? It has a slope. So you can have some fun figuring out how to do that. Anyone who can do that, we'll do a dinner. Okay? At some nice restaurant.
Yeah,
Okay,
can I make a
so-
suggestion for you guys who learn Mathematica already?
You
All
can
this.
do it with him. Yeah, you can do it together. You can work in a group. That would be fun if you could do it all together. That would be great. So please do this assignment. That'll get you the surface to volume, inauguration, as it were. So remember, okay, you have diameter. So the surface to volume here is h over d. I mean the aspect ratio, height over diameter. It's also height over diameter here. But here you also have slope. So figure out how that works, because you have to define the cone. The aspect ratio is not enough. You need one more parameter to define a cone. All right. So that would be a great project for your math program to see if you can. Now I worked it out, and then of course take the derivative. Let's find the minimum. And then the last part of it, don't forget, plot all 3. So plot the first one, the rectangular solid, plot the cylindrical, right solid, and then plot the cone. Where do you think the cone would be? Not an easy question. Now, obviously, we eliminated one more flat surface. Still, when I plotted, I'm not going to say what happened when I did it. I'm not sure I did it right. But if you can do your program here, maybe you can get a better result. Okay, so do this like a homework, okay?
Just based on symmetry, it should be somewhere in between, right?
Well, you know, this is, I mean, I agree, it could be, but the cylinder has two flat surfaces and the cone has only one flat surface, the bottom, the base. Where would it fit in if you plot those three graphs? I'll send you what I got. You can see for yourself, and you can plot it with Mathematica. That would be a great little. Okay, so let's do that. Let's do that. Get whatever you have time. Okay. Plot all three. Take the derivatives, circular symmetry, and answer these questions, right? What do you think of? Okay, nanomaterials do come in the shape of cones. They do come in the shape of cubes. They do come in the shape of needles. And either for catalytic activity, advanced surfaces, optoelectronic properties, all very important, very dependent on the shape of the nanomaterial. Let me show you. You can see up here, there's a cone. Now these are bigger than nanomaterials, but this is a micron size thing. But nonetheless, we can make cones. Here you have cylinders, and apparently the conical crystal silicon pillars formed by lithography, iron oxide cubes, and the cube kind of tells you it's either FCC or BCC structure. We'll get into that. And why don't we form rectangles? You rarely see rectangular nanomaterial. Why don't we see rectangles? We see cubes all the time, but not so much rectangles. I mean, they exist too, but not under different circumstances.
If you have the same elements, there's no reason why one bond side would be shorter than the other. Or...
Where's the cube here? It's right here, right? Transfer that to energy, you don't have to lose the energy. So it's not going to be as reactive as a rectangle. When the rectangle is being formed, it's going to decompose into a cube every time. So this happens in the real world. This is your simple algebra being converted to real life, real lab situations. Bottom of the curve, it's a cube. We just proved that 1.24.
If the bonds do not form the cube, but maybe form something like that, it's still going to be regular shape, right?
It can be, it depends on a lot of things. Iron oxide is a different electronic structure. To tell you exactly why something forms as a cube as opposed to an octahedron, that's hard to do. For example, a lot of metals either form as hexagonal close packed, base-centered cubic, and body-centered cubic. That's it. The simple cube, which is A layers, there's only one element that forms that, right? Polonium. So these things are a little more, you have to do the quantum mechanics and whatever to figure that out. But obviously, they like to form cubes rather than rectangles. And then over on this side of the pillars are being, okay, we got like say cubes. Conical acoustics, gallium arsenide, aluminum gallium arsenide, core shell nanoscale. So those guys are wires that have incredibly high aspect ratio. And carbon nanotubes too have an aspect ratio of 1,000 and more, 50,000 even we've made. So you can see nanomaterials are indeed, and this is just an example of some of them. You have dodecahedrons, tetrahedrons, you have every platonic solid, every Archimedean solid, icosahedrons, the octahedrons, etc., etc., etc. Okay. There are some, again, is the sphere a platonic solid? You studied platonic solid? These are them right here. What's the definition of a platonic solid? Is all sides are equal, all angles are equal. But the sphere is not. The sphere is not a platonic solid. It's just there for reference. Archimedean solids often are these what are called truncated. So you take a cube and you cut off the corner. And or you take a icosahedron and cut off the tips. You get different kinds of structures. So you can look at these, you can see this one here has a lot of faces, assuming again all are equal volume. You would imagine this one has the lowest surface to volume ratio. Whereas the truncated tetrahedron looks pretty reactive, as does the tetrahedron. All right, you can get a little bit of a flavor of all the different kinds of materials and the shapes that is, and there's even more. This is just the simplest examples. There's some very complex geometric figures. And I'll tell you one thing, there's in solid state physics, there's to make things really crazy is what's called reciprocal space. And that's basically the space where electrons and light exist. You have the atomic structure, that's crystallography, right? The reciprocal space is where all the electronic action takes place. The geometry of that is insane. So this is easy compared to that. We did write a chapter on that, and I'll talk to you about that too. Okay, so geometry is extremely important because it's important to the physicist, it's important to the chemist, and it's important to the engineer. I see, I made some spherical particles, but I can't bond them to a surface. Well, make hemispherical particles, and then you have a flat surface with flat surface. The flat surface is more reactive, and maybe it will bond. So you can use this principle in polymer chemistry too. If you understand the energetics of a material, you can do things. There's our cube octahedron, and we're going to focus on that today in later examples. And if I plot the number of faces versus the normalized surface area, I get this. I get our Archimedean solids and Platonic solids. And that looks, remember, we only stopped at 100. And the sphere has how many? Looks like we're converging pretty much with the spherical limit. Close enough. That's the way my computer drew everything. So that's obviously it was just interpolation. All right, everyone got that? It's good, straightforward stuff. And how many of you, by the way, are in the health program here? That plan to go on in health sciences, or what is your program? Anyone going on into the health sciences, and how about sustainability? What are the 4 major programs here you have?
We have applied digital intelligence, and then the smart cities and sustainability
cities
are kind of merged now.
Right.
And the other one is the health science.
3.
It's now.
So you guys you haven't chosen yet. You haven't made up your mind which way you're going to go. Huh?
Sustainability.
Sustainability. Okay, there's a lot of, like we said, a lot of nanotechnology involved in sustainability. So it's good to have at least exposure to this course, and I think. That you get a good feel for that. Okay, so here's a graph of what we just looked at. Okay, approximations of numbers of atoms. Okay, this is always a good one. And it's used by physicists all the time in their theoretical simulations. So again, it's algebra. We want to know how many atoms are in a cluster. It's a spherical cluster approximation, which means we're only going to look at spherical things. All right, and this is without packing fraction. So this is with no spaces inside the cluster. I actually found a way to use different volume packing fractions and come up with more realistic numbers. But anyway, it's just, you can go through this. You can see the volume is simply the number of atoms times the volume of each atom. And it ends up being a ratio. The number of atoms is just a ratio between the two. Once you take the cube root of that, the radius of the cluster divided by the radius of the atom. That's as simple as that. The surface of the cluster, once you, again, just go through the algebra here. 4 pi r squared, and here we have r.
So what's Na again?
Na is the number of atoms, sorry. So, yeah, N number of atoms, Vc is the volume of the cluster, Rc is the radius of the cluster. Little r, A is the radius of the atom. Okay, so the radius of the cluster in terms of the radius times the number of the cube root of the number. It's just algebra. You can go through and prove that to yourself. All right, so surface, the number of surface of the cluster atoms is 4 pi r squared times Na to the 2/3. Again, in terms of the atoms, the number of surface atoms is simply the surface of the cluster divided by must be. Sometimes I do this in the middle of the night and okay, whatever happened, that answer is correct. So again, go through the algebra, please, for yourselves. It should work. And it turns out the fraction of the surface atoms, which is what we were interested in, is simply the number of surface atoms of the cluster divided by the number of atoms total, and you get that number. 4 divided by cube root of Na. Okay? That's just a spherical cluster approximation. Please just go through the algebra yourselves. It just, I'm not baffled. Yeah, I think that was about A. We were kind of lost. I suppose this must be the area of A. Yeah, this is the area of each atom. All right, okay, that's what that is. I should have used the N or something. Okay, whatever. The fraction of surface atoms is that number there. If you add packing fraction, then that number increases. All right, the surface area increases. Okay, so this is just a simple thing that physicists use for their project. Physicists love spheres and they love vacuums. Things working with spheres and vacuums, easiest to work with. Okay, so 4 to the minus Na to the minus 2/3. But in reality, the spherical cluster approximation, if you plot it versus the reciprocal of a cube root of the number of atoms, you get a line. All right, this is surface fraction. You get a line. However, in reality, if you look at a cube octahedron, as it gets smaller, remember it's going smaller this way, larger this way. The smaller it is, it deviates from the ideal situation. So the spherical cluster approximation is very accurate for large clusters, larger clusters, more than 1,000 of atoms. Okay, so this is a useful tool, and we can calculate the number of atoms on the surface, compare that with other ways to do absolute surface atoms with the cubic meter you have right there. So that's, I thought I'd bring that up and show you that too. Just again, just a little simple, more algebra. Oops. Okay, so we're done. Okay, so don't forget your surface was spelled wrong. Collective surface area is a fundamental characteristic of nanomaterials that offers great advantages in catalysis, interfacial bonding, biological system. The polymer chemist, and please correct me if I'm wrong, is very interested in interfacial bonding. If I'm adding nanomaterials to a material, let's say, for example, we add an equivalent mass of micron-sized materials and nanomaterials or nanomaterials to a polymer, which one will have more interfacial surface area? Obviously, the nanomaterials by a tremendous amount. Micron-sized materials have larger surfaces, but much smaller surface to area, surface to volume ratio. All right, they're more stable. So you want to put smaller and smaller particles, you have a lot more collective surface area for one thing. And plus you have probably stronger reaction. So you chemically modify the nanoparticle with some linking group that links to the polymer. And then you mix it up with the polymer, cure it, whatever those guys do. And you have a stronger polymer. The scratch resistant coating is using nanoparticles, not micron-sized particles. Not only that, micron-sized particles scatter light very strongly, so you may be losing some of the clarity that you want under clear coating, whatever these guys have. All right, so interfacial surface area is very important in polymer chemistry, especially when it involves putting in carbon nanotubes or putting in silicon nanoparticles or whatever other kind of zinc oxide, things like that they like putting there. Nanoparticle size impacts surface to volume relationships. Extremely large particles have a much smaller surface to volume ratio. So even if I had a sphere, you saw, I think we had one diagram earlier, a sphere that gets smaller and smaller exponentially becomes much higher surface, collective surface area. The nanoparticle shape is determined by inherent material properties and energy distribution. So this is what we have in terms of our surface to volume ratio and particle shape. Two things, size affects surface to volume ratio as the particle shape. So we know the sphere is the ultimate shape, cube better than a rectangle. Yeah, comment on like that. Oh, okay. Let's see. Oh, very well. Okay, now let's go to the next adventure. Okay, this is going to be fun. Crystallography and some magic number clusters. The cluster you have there is made up of a magic number of atoms. That number there is 55. You say, what the heck, 55? That's a strange number, but it's a magic number. Let me see if that's where I start. Oh, we're going to get into that. Let me just go through this. You have to be a physicist. If you're a nanoscientist, you do have to be a physicist. You do have to be a chemist. You have to know mechanical engineering, electrical, optical engineering. You have to know biotechnology. You have to be a mathematician, really, to some degree. You have to know computer technology and program. You don't have to be a polymer chemist. You don't, no, just joking. Of course you do. You have to be a chemist as well. But you become you have to become a little bit of an expert in a lot of different fields. And this is one of them. You learn, make sure your mathematics is in good shape and you can navigate through all this stuff. It'll happen naturally, of course. Okay, so just some extremely basic crystallography. We're only going to work with what are called cubic systems. We're not going to work with biclinic or hexagonal systems or anything else. Only cubic systems. There's three kinds of cubic cells. One is the primitive cell. You can see it has 8 atoms. All right. The next is what's called the body-centered cell, or BCC. You can notice that it has 8 atoms, but it also has 1 atom in the middle. Simple as that. And then the third one is the face-centered cubic, which has the basic 8 atoms, but it has additional atoms on each face right in the middle. And how many is that? There's 6 faces, so there are 6 more atoms there. All right. And from this, we're only going to work with the face-centered system, the last one. Okay, everyone see this? This is it, basic crystallography. You're getting it right now. Body-centered cubic, you don't see many metals crystallized in body-centered cubic. Pardon me, simple cubic, because it's very unstable. There's a lot of space between them. Packing fraction is only about 60%. So there's only one metal that actually lives that way. The body-centered cubic is very popular. Okay, but it's not a close packed system. However, the face-centered cubic is a close packed system. You can kind of see here, it really is pretty tight. There's no, you can't see through it, and all the holes are plugged. And it's about 70. By the way, you can see cube, yeah. We've kind of a cube right here. This way, it looks very different. Right? And these layers, the face here is called the 1-1-1 face. The square face is called the 1-0-0 face. What does that mean? I forget to make a slide about this, but basically, let's do it here. If that's 0, okay, and 1-1-1 means, let's just go half this way, half this way, and half this way. It'll end up being a triangle inside. And if you build triangles to this corner, you have what we have there. If I start cutting off the corners, I actually see these triangles. So this is the 1-1-1 face. With the 1-0-0 face, you go 1 here and 0 on both ways. It's this face right here. All right. That's the one with the face center in it. But these things, when you overlap them, they all look like that. And I'll show you a buildup of how we make this crystal in just a minute. But that's all you have to know right now. This is the 1-1-1 face. This is the 1-0-0 face. That's based on the Miller index of the crystal. Okay, that's the only 2 faces we need to worry about. Okay, we'll reinforce this as we go on through the lectures. And then lattice constants, the side is equal to, if we say the radius, and remember, these are just points here, but in reality, you can see, they're touching. These 3 are touching, these are touching, okay? Just like they are there. So this is just to show you the points, okay? Just to show you the structure. And very importantly, the coordination number, which means how many atoms are connected to one atom, is 12. The atom in the very center of this is surrounded by 6, with 3 on top and 3 on the bottom. That's 12. The vertex atom is not surrounded by 12. So let's call, how many broken bonds are there for this atom? Can you figure that out? You look at the corner atoms. How many broken bonds are there? Okay, let's start okay, here. How many broken bonds are on this surface? If I cleave this surface. It's hard to visualize right now, but remember I said each atom is covered by 3 on top and 3 on the bottom. So there will be 3 broken bonds. This one doesn't have a middle one, so it's a little bit hard to see. But there are 3 broken bonds here. Here, how many broken bonds do we have? Basically, what we have, take this layer and we'll just superimpose it on this layer to fill the holes. So each one of these has touching 4 atoms. You can actually, it's better to see it underneath. Look, you can see 1, 2, 3, 4. Those bonds are broken on this layer. Not on the bottom layer, right? What about this? What? The edges? Edge. This one, okay, it's connected, but it's not broken. It's only the top ones that are broken. Remember, I'm cutting it. So I only remove every atom, I remove 4 atoms. Here, every atom I move 3 atoms. It's hard to see because there's nothing in the middle. But the edge atoms, it's much harder to see. You have 1, 2, 3, 4, and then there's actually 1 touching it. So there's 5 atoms you break for each edge atom. But for the corner atom, you break 7. It only touches, remember, it only touches 1, 2, 3, 4, 5. Everything else is gone. So there's 7 broken bonds here. 7 here. This one has 3. This one has 4. Pardon me. 7. This one has 5. This one has 4, and this face has 3. Look at you. You'll get a better picture in just a minute. Okay, so that's, I mean, basic crystallography. You can look at it this way. Here's another picture. We're looking at the FCC structure. So the A layer, which is this layer. This is the layer we're looking at right now, this one. The equatorial layer, okay? That's what we're looking at right here. So that's going to be which layer? The 111, right? So we start out here. Then we put on the B layer. And you can see, okay, this is black space, empty space. So I can put this B layer on top. You notice I still have some empty space, but half of them. Half of them are now covered, but half of them are still empty, uncovered. Now I have a choice. I can put the 3rd layer on top of this layer, directly on top, and I'll still have some holes, right? Or I can put the 3rd layer and cover those holes. So every layer is different. This is ABC, and this is ABAB. This is the hexagonal close pack, and this is the face centered close pack, which is that. That's it. That's all we have to know for crystallography for this. You can see there's a difference. These are very different because they crystallize in different things. The HCP is not a cuboctahedron, it's a hexagonal structure. So it depends on how you put the layers.
So just to backtrack to something.
Yeah.
These are all van der Waals, right?
No, these are regular metallic bonds.
Yeah, metallic bonds, okay.
Metallic bonds.
Okay.
So these are strong bonds. These are crystals, metallic solids. We're going to say we're working with gold.
I see.
No, van der Waals is more, you can have van der Waals bonding mainly between, like, for example, clusters of carbon. Tolerance, C60. Okay. Those are van der Waals bonded and they form the same kind of structures. And so you're right in a way, it depends on which material. Okay.
But most of the time we're talking about
This is
metal lattice.
We're looking at gold.
So,
Gold metal, but there are other van der Waals bonded clusters.
but covalent bonds don't play much role in
Covalent bonds are
at all.
they have different structure. Diamond. The diamond structure is very different. It's more of a 2 FCC intertwined. two FCC, it's much more hard to visualize.
But a lot of times it's between home and same element, they have.
Yeah, and the diamond is just pure carbon, but it's tetrahedral. Tetrahedral bonding, but its crystal structure is like two FCC intertwined, very strong. Okay, so you can see that we're going to work with the C layer type ABC polytype for FCC today. So you can see, start here. This is the 1-1-1 triangular face. You put one layer over it, you cover half the holes. You put another layer, you have an option to cover the holes or not. If you don't cover the holes, you have a hexagonal structure. If you do cover them, you have FCC structure. And this is one way to look at the 1-0-0 or 0-1-0. We don't care. It's just a family of 1-0-0. They're just planes that are, you can parallel planes, and then you can see the 1-1-1 or the triangular planes. You can see they come up to the corner, right? So there's a lot more to it, of course, the crystallography, why they call them 1-1-1 and 1-0-0. We don't have to get into that right now. Okay, so this is the two we're going to be most concerned with. Why? Because we want to build a cube octahedron. That's our goal today. And this is a cube. So you look at the cube again. If I look at the triangle at the corner, that's what I'm going to be cutting off. Truncating, you can call it truncating. And you can see I have a square face. I have 6 square faces and 8 triangular faces. Okay. See, this is good for your brain, by the way, honestly, because it activates this visual part of your brain. It relates it to an abstract part, which is mathematics. So you can see there's the 1-1-1 face and the 1-0-0. Why is this important? Well, in the next slide, we're going to look at energy. So we're connecting this all. We start with collective surface area, surface to volume ratio. Now we're looking more at crystallography, which involves atoms. And then our next slides will be about energy. Now we go into mathematics. Okay. I thought I had. Oh, here, that's coming. Let me show this slide right now, just to get ahead of the chase a little bit. Okay, so there's our atom. So that's going to be our central atom. Then we add a bunch of atoms, and you'll notice the central atom is covered by 6. This is in one plane. And then we'll put one more layer of atoms on the outside. You notice it's a hexagonal shape. You can look here. You look at it this you can see we have a hexagonal shape, right? Okay, that's what we have there right now. All right, now the next thing we're going to do, we're going to add these guys. And you see there's 3 atoms there, right? We're going to place those 3 atoms over the center atom. Now, why did I add more atoms? Because we're building a cube octahedron. So we have 3 atoms over the central atom, and you can see it covers half the holes, correct? Just like our A, B, C layer. So we cover half the holes. Now, we want to do FCC. So do we want to cover the remaining holes or not? Yes, we want to cover the remaining holes. So I made it red. So I made it red. It's equivalent to that one, but it has to be shifted. So I shift it and I cover all the holes. All the holes are covered. So now we have FCC, ABC. Now I add one more. Remember, every layer is 1 fewer atoms, right? So I have now only 6 atoms to cover the top. And I also have the same 6 to cover the bottom. Again, they have to be done properly, right? And we have to shift it this way and turn it this way. And then we have our cube octahedron. This is how it looks from here, or if it looks like this, here's our cube octahedron. Here's our 111 face. Here's the 100 faces, a family of them. The square faces, right? And then you can see the cube octahedron, right? That's what you have there.
None of them is on top of another one directly, right?
Huh?
There isn't a pair of them that's directly on top.
There's
right?
no more on top.
Yeah.
Wow, you know, and this is, I could put more here.
No, I mean for this unit,
Yeah,
you can't. There isn't one that's on top of another.
No.
It's always a little bit
they're all
off.
staggered. Yes, exactly. They're all covering bowls. But if it's one on top of another, that's a different
That would
material.
be like AB or something.
That would be, if it's right on top, it's A. But if it's always staggered, it's AB or ABC. And notice there's nothing on top of this. Why don't I put one more atom there?
It would be exactly opposites of repeat.
That'll be a very unstable atom. That'll have how many broken bonds? If I put one atom here, how many broken bonds would it have? If it's connected to 3, it would have 9 broken bonds. It would be totally unstable. The vertex atoms are already 7 broken bonds. All right. Okay, now let's get into what's called algebraic topology. What is topology? Topology is the study of surfaces, the mapping of surfaces mathematically. It's a huge field of study and a very important one, of course. So we start with polygons. Polygon, hexagon, etc., octagon, squares, triangles are where we start because it's simpler. All polygons are made up of what? Triangles, right? Every single polygon is made up of a triangle. Combinations of triangles, correct? So mathematically, we can describe all polygons with triangles. We're only going to look at what are called convex polygons. And convex polygons, all the angles are less than 180. So they're kind of more, everything is internalized, if you want to look at it that way. Like, for example, a star is a concave polygon. And that's not what we're interested in today. Okay, so we have a lot of nanomaterials are 2-dimensional. We talked about graphene, which is a hexagonal type of material, and other kinds of polygons, they're octagonal nanomaterials that are 2-dimensional. So what is that? Let's talk about what is a magic number. A magic number is the number of atoms that fills a layer or shell completely. This leads to chemical stability, a major issue for nanomaterials. The general formula for a polygon is given here. But before we do that, I mentioned if I put, it looks like I have a perfect place for one atom right there, right? Why isn't that atom a good atom? Well, if I put it there, first of all, it's not going to be a magic number. Secondly, it's not stable. This is 55 gold atoms. It happens to be very stable, relatively stable always. This would be 56. That doesn't work. If I do what's called mass spectrometry, mass spectrometry can measure the cluster, right? The cluster of 55 gold atoms is this strong signal, and the cluster of 56 is like here. It does exist briefly, but it's not stable. I can put atoms here, not stable. You know, I can put one here, no, it doesn't work. This works. This is the 55 atoms. The first magic number is 1, right? There's one atom in the center. The second one is what? And you should be able to answer this. What is the coordination number of gold? 12. So you have 1, so the first one is obviously 12. So the first magic number is 13. 1, 13. Second one is 55. If I surround this with one more shell, I think it's 147. We'll get there in a minute. All right, so these are magic numbers.
So this is K with the 3.
And the K would be, right, exactly. K equals 0 is one atom. K equals, the shell index we're going to define just shortly. And each, this atom is like an onion. You peel away the onion to get to the central atom. Every layer, onion. Every layer is a magic number. It's more stable than the others. And so here this is our first topological equation. MK, we'll call it magic number. K is the shell index, which is simply the number of shells, starting with K equals 0. K equals 0, K equals 1, is the magic number is 13. So if we were to, well, we'll get you the formula in a minute. But if we were to plug in 1 into the formula that we're going to look at shortly, we'll get 13. And, you know, this is the beauty of mathematics. Honestly, it's just the symmetry and all of that just all come together, come up with these beautiful equations.
You can stack AB, you still have the same formula?
Yeah, this is now polygons. So we have two kinds of polygons, one that is vertex or origin. So you build like from a triangle, one triangle, add more triangles and more triangles, right? That's a vertex. Or you can have a center triangle, where you start with one atom in the center and build triangles out that way. This is good for all polygons. The formula for polyhedra is, of course, a little more complicated, but nonetheless. All right, so this is the formula. F and P are the K, we understand. K is the number of shells. F and P mean F is the number of faces. P is the number of sides. So for one triangle, F equals 1 and P equals 3. So let's do that real quick. K equals, for the first level is K equals 1. So we have 1/2 times face 1 divided by 2 plus, you can work this out real quick, right, on paper. And you should end up with 3. Right? K is 1, F is 1, and P is 3. What do you get? Should get 3. I'll tell you the first magic number for triangles. Is that correct? Did we do it correctly? Somebody work it out. Somebody work it out. Is it correct? Yeah. Okay. So our first magic number is 3. What's the next one? So if I guess I should show you a picture. Would help. Okay, you can write this down if you want. Okay, everyone memorized it? Okay. All right, so now we go to we look at this picture. There's K equals 0, M equals 1. I'll go back here. If K equals 0 and M is 1. Okay, if K equals 1, M equals 3. Okay, let me first finish this slide. SK is simply the number of perimeter atoms or boundary atoms. That's simply P, which we said for this kind of triangle is 3. And it's just 3 times K. So for the second set of triangles, K is 2, there should be 6 perimeter atoms. For the second kind of triangle, F and K are constant for what kind of triangle? We're looking at the vertex origin triangle. So if K is 2, okay, F is still 1. Someone do their head, I can't do. What is the answer? And then I at the bottom, you can't see really good, huh? I is the interior. So you take MK minus SK and you get IK, which is just the number of interior atoms. So these work. You can prove it to yourself. So you can see that for K equals 1 and K, there's 3 magic numbers. And of course, there's boundary atoms are also 3. For K equals 2, the boundary atoms should be 6. I made a mistake. All right? Yeah, I just made a mistake. Should be 6. Sorry. MK is 6 and boundary atoms are 6. However, when K equals 3, we have our first central atom. MK is 10 and SK is 9. And this is just nice simple polygon. This obviously this vertex origin triangle is a polygon made up of other triangles. All right. So this is we can call these just mathematically magic numbers. We don't know any maybe structures that are actually like this. A 3, magic number of 3 would be, I think, very unstable. And it's not, we don't consider them chemically stable. So these are more abstract. When we get to the polyhedra, we'll get more into the chemical stability. Now, with increasing K, MK becomes 1, 3, 6, 10, 15, 21, 22, 36. Does that remind you of anything? Does that sequence remind you of anything? Think back to your basic algebra. Pascal triangle, yeah, absolutely. Just beautiful. It's just, I mean, I wish I were a mathematician, but I was lazy when I was a boy. Hated math, and now I regret not going into math. But anyway, you can see how that works. So this is, we're starting with a vertex, and we're building from there. Euler's polygon formula, and Euler was, of course, one of the greatest mathematicians. He came up with the most beautiful mathematical equation, e to the I pi, right?
There's a typo.
Where?
F, you need an F.
Somewhere?
See, Euler only did an F.
Euler's polygon formula, where?
You have two V's. You need an F.
Where do you see the edges? Oh, I think that should be VF. Yeah, sorry, thank you. Thank you. Here's when he came up with this equation, of course, e to the I pi, right, or minus I pi, I can't remember which, equals what? 0 or 1?
Minus e to the minus I equal to pi.
I pi equals minus.
Yeah,
Anyway,
yeah,
but it's got e in it, which is a natural
minus
order.
I.
It's got I, it's got pi, it has 1, and it has 0. The 5 most fundamental things in math. One equation. This was what, 1700s? But anyway, he said that the total vertices minus all the edges plus all the faces, sorry about the V there, is equal to 1. And it all applies to this stuff. Now we can prove, I'll send you the paper where I took all this stuff from, and we can prove this equation, MK, using Euler's formula. We're not going to go through it here, but it is in my new book, which is coming out this year. So I actually worked it out and proved it. But this is the kind of formulas that we're going to use for also polyhedra. Okay? So the number of polygons, let's do a little bit of, again, there's another famous mathematician called Gauss. And they asked him to, what is the sum of all the numbers between 1 and 100? 2 seconds later, he said, well, it's 5,050. Like I said, how the heck do you do that in 1 second? Well, he took one series and then he reversed it and created a new equation to go backwards. So MK here, you can see, we can say the series is K plus 1, because actually, when you look at the triangle, the side is equal to K plus 1. If K is equal to 2, K plus 1 equals to 3, right? Right? So what we can do here is sum K plus 1, 1, 2, 3, 4, plus K plus 1 all the way to the end. And if you do it this way, you go this way and then you flip it around and then add up everything, you get your answer. You see 1, 2, 3, 4, how many times do we have that, right? And we end up getting K plus 1 times K plus 2 over 2. And this is our equation. 1/2 K squared plus 3K plus 2. This is the same as the polygon equation. You can prove that for yourself. It's the exact same thing. Because remember, P and K are very specific for a certain kind of triangle. Okay, so this is one way to kind of prove it. Okay, this is enough for polygons. We want to focus on our cube octahedron. Everyone okay with this? It's just a simple series. Again, the best thing for guys to do is just do it. Just work it out yourself. Just do it yourself. Tell your girlfriend, God, I love you very much. I've got to work out Euler's formula tonight. Okay, see what she said. Maybe she'll say, God, you're amazing. I'm going to help you. I'm going to work with you. And you're going to boom like that. Wedding bells, man. Wedding bells. Okay. Next thing you know. All right. So this is a very simple way to do things with Euler, Gauss's. There's a little kid when he did this, you know, just for now. There's other ways, of course, there's other ways. And go ahead and show to yourself that this equation is the same thing as what we just showed, using F equals 1 and P equals 3. All right, it would be the same. Actually, you can kind of see it right now. Here, F equals 1 and P equals 3, right? It's in there. If you divide by, you know, it's the same. Okay, take that out. Okay, but what we are most interested in is polyhedra right now, today. Gold 55 cluster. And actually, when I was in Germany, I was doing a postdoc. Have time. And we were working on synthesizing gold 55 crystals and then adding ligands, organic ligands, to stabilize the cluster. We added triphenylphosphine, and then there's other ligand exchange reactions you can do and then bind them to polymers. So you first synthesize with one ligand and then you exchange the ligand. A ligand is simply usually an organic chemical that can bond to the vertex. So how many bonds if we bond to the vertex, how many bonds does gold 55 make? Okay, how many corners are there? Now you gotta be careful not to count atoms twice.
Both ends.
Almost 12. 12. Okay, so you have 12. So triphenylphosphine will bond to one vertex atom, so you have 12 of those. So the chemical formula is gold 55, 12, blah, 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 and then some stabilizing cation. So again, a lot of chemistry, we have to know, oh, this has 7 broken bonds. So as a chemist, you can say, I can bond to that. because it needs a bond, it needs many bonds. All right, so the cube octahedron, we like the 55 atom today. Again, K equals 0, M equals 1. And there's a whole other formula for polyhedra. K equals 1, M equals 13. K equals 2, M equals 55, 147, 309, 561. And on like that. So Euler's formula for the shells now we're not just talking about layers, we're talking about shells, is total vertices minus the total number of edges plus the total number of faces equals 2. This is just, the ancient Greeks and others, I know in India they just took spheres and made polygons out of them, and made polyhedra out of them. And I think they came up with this formula this long time ago. But for a cube octahedron, obviously we have 12 vertices, we have 24 edges and 14 faces, and we end up with 2. Let's see. Now, we said that triangles are the building blocks of polygons. I didn't show you all the other polygons. When I get my copy of my book, I'll send you a copy. You guys, since you attended class, you get copies. Okay. Make sure you give me your email addresses. When we said the triangle was the building block of the polygon, well, the building block of the polyhedron is the tetrahedron. In other words, I can take this octahedron and break it up into how many tetrahedra. Now, if I say that the tetrahedra's vertex is at the center of the atom, center of the cluster, how many tetrahedra can I make from that? Obviously, there's one here, right? There's 3 sides here, 4 sides. If I go to the center and make that a vertex, I have 4 sides, correct? So I already have how many? That's how many corners? 8. 8. Now, how do I get some more tetrahedra out of this? I can take the square and divide it into 2. There'll be 2 more tetrahedra. So how many total tetrahedra do I have? Everything converges to the center. I have 8 corner tetrahedra. 12 of the others, exactly. I have 20. And that's going to be in the polyhedron equation. All right, so these are all made of tetrahedra. As long as you have a center atom, it's easy to do. Just like we did triangles earlier, now we do tetrahedra. Okay, here you go. You may not have known this about the Pascal triangle, but it's one of the most brilliant. I mean, you're just looking at the most brilliant things. These numbers here, the 1, 3, 6, and 15, 20, those are called the triangle numbers. All right, triangle numbers. You can see that those what those are. That the tetragonal numbers are 1, 4, 10, 20, 35, 56, and 84. But don't say these are not necessarily magic numbers. It would depend on the structure. These are for tetrahedron. But nonetheless, that's the basis, the algebra that will now be transformed into other polyhedra. And of course, you can do pentatopic numbers all the way down to bigger and bigger and bigger numbers. 1, 8, 36, look at that, 1, 7, 28, just beyond my mathematical skills. But keep this is again, just Pascal, another brilliant mathematician, just comes up with this triangle, and it's a fundamental for so many things. These are my sorry drawings of cube octahedra, and I need better ones. Okay, so we're going to do This is MK. I'm not going to give you the general polygon equation, polyhedral equation. It is just too involved. I will send you a paper that you can read for yourself if you're interested. I definitely will send you. But this is the end result of that equation. The equation for the magic numbers of a cube octahedron is 1/3 times 10k cubed plus 15k squared plus 11k plus 3. All right. The surface numbers as a function of k is 10k squared plus 2. Okay, so if we say this is a cube octahedron, k is what? 1, 2, 3. 0 was 1, 2 was 12, 13. This is 3. So plug in 3 into that. What do you get? 10 was k cubed. 3 times 3 is 9. I mean, let's do the surface, right? 10 k squared. K is 2, right? What is it? SK, let's do that first. It's 42. K squared is 4, 10. So there should be 42 atoms on the surface, right? How about what's 42 plus 13? 55. So if I plug in 2 over there, I'm going to get 55. All right? That's how nicely these things work out. So we have 42 atoms on the surface. The next shell will have a whole lot more. So here are the magic numbers for cube octahedron. We can get bigger and bigger. But what we're going to do now is we're going to derive that equation from what I call the method of brute force. Nothing, no polygon equation, nothing. We're going to derive it from the basics, the most basic things. Okay, you saw this already, so you can understand. You can build a cube octahedron. So our last thing in this lecture, we want to derive it by the method of brute force. The formula for magic numbers is boom, 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 and the shell number. So what we're going to do first is derive the shell, because that's what we can see. Technically, we cannot see inside. And then once we derive the formula for the shell, how can we find the whole thing? What can we do to find the whole thing? The mathematical, obvious mathematical manipulation to derive the whole 55.
K minus 1 as an interior.
Well, you're almost there. It's just the shell is 10 squared plus 2 for every shell, right? So what do we do mathematically to get the whole number? We do a series. We just do a series. Pardon me, summation. Not a series. We do a summation. All right, so let's do 10 squared first. Let's see what we get. Okay, there are 12 vertices, period. No matter how big the cluster, you always have 12 vertices. So let's do the next easiest one, is the square faces. The number of edge atoms is always k plus 1. With every increase in the shell number, we add 1 atom to the edge. Go back to my picture. Okay, let's see, it's not so easy. Okay, we'll do the first 2, right? 2. Here's 3. Here's 4. Here's 5. Here's 6. Here's 7. 1, 2, 3, 4, 5, 6, 7. Here's 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So every cell is k plus 1. K, cannot do it by my head. So here, 55, k is 2.
3.
So k plus 1 is 3. That's the edge for k for 55 atom cluster. For 3, k is 3. There's 4 atoms, so k plus 1 is the number of atoms on the edge. Okay. We cannot count any atom more than once, however. So we want each edge atom to be purely an edge atom. So we need to subtract vertex atoms from each edge. So there are 2 vertex atoms on each edge. Now this is what I mean by the method of brute force. This is just observation and induction, right? Inducing the next step from the top down, right?
Oh, so the strategy is based on this. We have k equal to 2, and then do the induction on k.
Yeah, that's it, basically in a nutshell. So we have to subtract the vertex atoms. So we cannot count any atom twice. We want each edge atom to be purely an edge atom. We need to subtract vertex atoms. So there are 24 edges. So the number of edges, edge atoms equals k plus 1. However, the number of total pure edge atoms is how many edges are there? Remember Euler's formula? 24 edges times 2 minus the number of edge atoms. So it's k plus 1 minus 2 equals 24 times k minus 1 equals 24k minus 24. So that's how we say that's the number of what are pure edge atoms.
Meaning that the one that defines the edge, but not at the tip.
Right. No vertex atom. You cannot. Let me go back to my picture here. Okay, this is an edge atom, right? This is also an edge atom. These atoms are all shared.
It's
So
5
these are
minus
vertex
2.
atoms. You gotta just subtract them. So here we have, there are
5
5.
times 2.
4 plus 1 is 5. But there are 3 edge atoms that are pure edge atoms, no sharing of anything. Now they share edges. That's another story. We'll get to that soon. They share edges, but they don't share the vertex atom. So the number of see again, I did this, so we have to check with your program because there's a lot of sharing going on here. You have to filter that out. So I'm going to say the total number of edge atoms is 24k minus 24. So we can check that. Yeah, we can check that by how many edges we have there. We have 24 edges, and k is 3. Anyway,
Yeah, okay.
I can't do it. Okay, but all I know is that we have to make sure that and the shared edges and whatever we have to reconcile. But the edge is independent because there are 24 edges. That's just the way it is. So if k is 24, I mean, pardon me, if k is first 1, 2, 2, for 2, right? That's 48 minus 20. There should be 24 pure edge atoms on that, and that makes sense. Because there's only one pure atom and there's 24 edges. See? That makes sense. Okay, that's good. Okay, you can see this is the only pure atom that has no vertex. There are 24 edges, so there's 24 of these. Now we have 12 vertices and 24 edge atoms. We got those taken care of. Okay, okay. Okay, now I just find this very much fun. I hope you guys enjoy it too. All right, so we came up with 2 equations. One is 12, and the other one is 24 minus k, right? Minus 24. Now the square face. Again, we don't want edge atoms in it, and we don't want vertex atoms because those are already taken. So we need only what are called pure pure face atoms, the ones that are only pure. So we take the square. Edge atoms squared is k plus 1 squared, right? However, we need to find a number of atoms that are purely face atoms, those that do not share a vertex or an edge. So this is the brute force method, Dr. Punja. This is just from no equation.
Now we
nothing.
got the 9, but we have to take out the 8.
So now we have to take out the edges and the vertices. So by observation, we see that the number of atoms in the interior square is always defined by k plus 1 minus 2. Where did I get that? We're always subtracting the 2 edge atoms. K plus 1 minus 2. Does that make sense? Each edge. Anyway, okay, so there are 6 100 faces of a cube octahedron. And this yields 6k squared minus 12k plus 6. So if k is 1, okay, all I know is it works. So let's go through.
We got 6 of those guys.
Okay, so anyway, there are 6 100 faces of a cube octahedron. This yields the number of atoms in the interior square is defined by k minus 2. And that makes sense because if k is 2, which is there's no interior, yeah. Look at it this way, guys. Okay, so far so good. K is 2. We have 55 atoms, right? Correct? Should be one atom in the middle here somewhere.
Yeah, it is because k is equal to 2, you add 1 equal to 3, and then you subtract
Okay,
2,
plus 1.
so you get 1.
And you get 1 in the middle. It works.
Yeah,
Thank
and
you.
there are 6 of them.
Okay, got it. You can see this is good for your brain, huh? Don't you think? You gotta do this. It keeps your brain active. So you got 1 left. The other ones you have more than 1. You have 4. Okay, so there's our next equation. So our last equation that we need is the triangle face. And we're going to use the polygon formula. We already know it. Why not just use it? We have a formula for the interior number of interior atoms. We multiply it by 8. And then our formula is 4k squared minus 12k plus 8. All right. Okay, now what do we do? Everyone see that? This is from our polygon formula. If you recall, let me go back. Remember, interior atoms are simply this formula minus right there. Minus the boundary atoms. And this is very convenient because all the boundary atoms are already shared on these cube octahedra. Okay, so we use that formula, very simple. And we have 4k squared minus 12k plus 8. Now, we put it all together. The grand sum of all surface atoms is n surface equals vertex atoms, corner atoms, plus the total of edge atoms, the total square atoms, and I should have said pure square, not total. Okay, I'll have to change that. And then the total of the triangle pure atoms. I make the substitutions into that equation, 12 plus 24k minus k, plus the number of vertex atoms. Which one is which, I don't know. And then add it up. What happens is you get the formula 10 squared, 10k squared. I was really sweating it out when I did this because I'm going, oh God, I hope this works. Okay, now we're here. Now we have the number of shell atoms. Where do we go from here? We have to do sums.
K to 1.
Okay, we just do a sum. Any way you want to do, there's a few different ways to do it. This is what we want. Remember, we have 1 in the center, And then we sum the shells, x k squared plus 2. Again, I want to do what about mathematics and all of this. And if I did it correctly, I did it correctly. We just, I want to, these things all look kind of familiar. And we reduce all the summation terms, and we did this, which is the goal. So just without knowing any polyhedral formula or anything. And by the way, this is a simple pedagogical paper that we can do if you're interested. And this is formula only for cube octahedron. There's other formulas for all the other shapes, and so we have reached the goal. Okay, this is by just inspection and induction. We look at it and say, okay, we're here, we don't share, we do the internal atoms, sum, and we get our result. Okay, we learned a little let's take a break. We learned a little crystallography. We became mathematicians and engaged in some algebraic topology. The vertex triangle and the cube octahedron became more familiar to us. These structures impact the properties of nanomaterials. Remember polygon rules and a polygon formula for triangles can do everything. And if you want to dig into why tetrahedra build these materials, you have to read this other paper. I'll send to you if you're interested. Most importantly, to those who are brilliant at math, programming, you can program all this stuff and you can be right on top of the world. Okay, let's take a break.